Pablo, the floor is yours.
Thank you. Thanks a lot. So first of all, thank you for inviting me to be here. I really like this place, and I hope I can chat with you after this talk. So this is like it's a bit quite different topic than the previous talk. So I will give like a broad intro. But if you are interested in the details, we can go over details later. So I'm going to tell you about what I've been doing mostly during my PhD studies, and I focus on out-of-equilibrium behavior of quantum many-body systems. And hopefully, by the end of this talk, you can easily interpret what this picture means, that this would basically appear in the front page. So we have had really nice talks about mostly solid-state materials, where our goal is characterizing or seeing novel phenomena. Mostly like condensed matter physicists, we have kind of traditionally focused, say, on equilibrium properties, like, I don't know, fractional quantum Hall effect or discovery of high temperature superconductivity. But in the recent years, there has been like this flourishing development of new experimental platforms that allows you to also kind of manipulate and have a quite level of control and tunability over your system parameters, which can be regarded as pretty good approximation as isolated from the environment. And because of this allows you to study not only kind of existing materials, but also synthesize kind of new kind of quantum matter and ask questions about not only equilibrium, but actually also about out-of-equilibrium behavior. So for example, in the last, so these platforms no, that was not the bottom. These platforms included, like, for example, trapions, river atoms, ultracold atoms, and a plethora of other platforms. And so, for example, in the last, I was saying, last couple of years, we have seen kind of first step towards realizing novel topological phases of matter in this Google or Quantinuum and a bunch of different experiments. We will hear, I guess, in the last day by Federica, realization of the first steps towards lattice gauge theories, and also understanding out-of-equilibrium behavior. And that will be the main focus of my talk. So in this context, one of the kind of relevant questions to ask is, when does a closed quantum many-body system thermalize? So at first glance, this sounds like a really weird question, because we are usually, we are used to think about the StatMech setup, where we have a system, we have a reservoir, and we exchange particle number, energy with this reservoir, and then we keep asking questions about the system. However, here we have a closed system, so if we prepare some initial pure state, it will remain being pure over the whole unitary time evolution. So what does it mean to quantum thermalize? So quantum thermalization refers to the behavior of few body observables, say magnetization, local densities, and observables like that, for sufficiently long times. So imagine we prepare some initial state. You prepare, say, this is a spin system, a chain, and you prepare some product initial state, some local spin degrees of freedom, and then you let it evolve as some generic interacting Hamiltonian. What will usually happen is that, please go ahead.
Just a short question. Is it a one-dimensional system?
It's a one-dimensional system in this plot. Okay. But it's in this plot. It doesn't matter. Okay? Perhaps in that, just to make sure, it's in this plot one-dimensional system, and most of the simulations, and the reason we usually focus on one-dimensional systems, or one of the reasons, is like we have really good numerical methods, such that we can kind of compare and we can check what we're doing. So usually what happens in a generic system is like correlations completely spread over the system. Every local degree of freedom becomes highly entangled with the rest. And if you wait for sufficiently long, what you will find is the reduced density metrics in such a small region tend towards some thermal density metrics, such that at sufficiently long times, expectation value of local observables tend to these thermal expectation values. So this is what we usually refer as quantum thermalization, and so far I'm being really, really rough. Our best understanding, and understanding in quotations, of how this process and why this happens is the so-called eigenstate thermalization hypothesis. And basically this tells you that the reason why systems look thermal at sufficiently long times is because eigenstates of the many-body Hamiltonian, they are like thermal ensembles on their own. So this basically means that if you compute, say, the expectation value of a few body observable, again, magnetization, density, this is only a smooth function of the energy density, so temperature or so chemical potential or some other intensive parameters that you would usually associate with a StatMech. But it doesn't depend on any kind of other properties. So in particular, if you have two eigenstates that are close in energy, the expectation value of these two eigenstates will be rather close. Oh, sorry, I keep pressing. And it also tells you, the ETH, it tells you that actually the eigenstate fluctuations are exponentially small in the volume of the system. So then to the question, when does a closed quantum many-body system thermalize, we have different answers. Generically, what we can say is that systems, most of the systems thermalize. If you take your experiment, you prepare some initial state, you let it relax, you usually can approximate whatever happens locally by some thermal density metrics or by some thermal expectation value. And in this sense, what you would expect is really observables relaxed to those thermal values, and eigenstates look thermal in the sense of ETH. So you can think that we prepare some initial state that was kind of short range correlated, some product initial state. We let the system evolve, and then this kind of correlations is spread completely over the system. This is kind of a cartoon picture. It's trying to relate to what usually we do in a StatMech. Okay. However, in the completely opposite side of these possible answers is the so-called many-body localization, which appears when you put a strong disorder potential in your system. So what you will find here is that it's a strong memory of the initial configuration. So at long times, observables don't look to relax to anything that you can approximate by some thermal value. And this usually appears as that eigenstates of the Hamiltonian do not satisfy ETH, which is usually said, they are usually said not to be thermal. So in this sense, in mind, you have a gas of particles. You put all the particles on the corner. You would usually expect particles spread around. But in the MBL system, they kind of stay there, and they don't want to move that corner. Okay? So in the recent years, there have been this question whether, is there a way to avoid thermalization, but without, say, putting a strong disorder potential, say, in a clean system? And different possibilities that could exist. So in mind, say, most of your initial states will thermalize, but for some reason, some initial states don't. And this was partially inspired by some, keep pressing. This was partially inspired by some previous work on like actual experimental work, where we have these Rydberg chains. So really roughly, these are systems that for some reason, if you put two atoms nearby, they don't want both to be in excited state. If one is excited, the neighbors have to be in the ground state. And because of these constraints, they observed that the system had really problems to thermalize as we would expect in a generic system. So however, what I followed during my PhD was some, I think I'm showing different slides that I can see here. Okay. Sorry for that. Yeah, I shouldn't see this. So I'm in the PhD, I focus on so-called fractonic systems. So in mind that for some reason, that we will see how, it approximately or artificially, we impose not only kind of usual conserved quantities, like particle number or total magnetization, but in mind we could impose that also the center of mass or the dipole moment of this charge is conserved. Okay? In mind, this could happen. So then if we have, say, a single charge in our system, well, this charge cannot move around because certainly it conserves the first quantity, but it doesn't conserve this one. This will vary this one. So the only way for this excitation to move is by emitting, say, a dipole in the opposite direction. So now the mobility of these guys really constrains the mobility of this. So you have a system that is highly constrained, and this really kind of basic and really basic observation gave rise to a plethora of different kind of phenomena that are completely based on this. For example, this was enough to find this fracton phases of matter, which is some generalized notion of topological order. This observation was useful to understand glassy behavior in strongly correlated materials. And finally, it was proposed that perhaps by just imposing in some way this conservation, this could be enough to give rise to localization in the same way as it happened for many-body localization. So what we did is trying to understand this in a really simple model that is amenable to kind of analytic computations and that we can easily simulate in our computer. And to do that, we will consider, and perhaps this is the first time we can make contact with magnetism, is that we will have, you might have a charge, you have a spin model, say on a chain, where your charge is going to be your local total magnetization, so sum of a set on the whole chain. And your dipole moment is going to be the kind of the center of mass or the dipole moment of the total charge. And we're going to have spin 1 degrees of freedom, such that spin up is going to mean plus charge, spin down is going to be minus charge, and spin 0 you can imagine as an empty side. Okay? So before, for example, we had this particular configuration where we saw everything was, say, empty except the central side. So this will correspond, say, to 0 everywhere, 0 spin everywhere except on the central side. So then you may ask, okay, which kind of model would allow, which kind of model would mimic this kind of dipole conserving systems in the same way that you would have the XY model for usual kind of magnetic system. So what would be the corresponding thing here? So this will be the kind of allowed terms where basically you have a charge or a spin that can only move around by emitting, say, a dipole in the opposite direction. So it keeps its kind of symmetric processes. Or a bound object of a plus and a minus that can, say, move to the left or to the right. Okay? However, we want to make sure that, the claim dipole conservation gives to localization should be universal for dipole conserving systems and not particular for specific models. So we want to make sure that whatever we find is generic. So to do that, we will consider, say, all possible families of Hamiltonians with these conserved quantities. And in particular, it will be sufficient to allow for this kind of longer range term, where now instead of acting on 3 sides, we'll be acting on 4 sides. Okay? So in mind, so we ask the question again, does the system thermalize, yes or no? And if you want to have some kind of picture of what is going on, you would like perhaps to look at dynamics. So you can look at 2-point correlations. So you measure the magnetization at site 0, at time 0, and you measure the response of the system at time t at site j, for example. So if you have a system that is thermalizing, and say you prepare the system at infinite temperature, such that every state participates in the same way, you would expect that quantities like these go to 0 at sufficiently long times. They simply decay. The system doesn't remember anything about this perturbation that you made at some particular point. However, if you run kind of your evolution for this Hamiltonian that we saw at first, this 3-side Hamiltonian, what you will find is that the correlations will decay, but eventually will saturate to a value that you can prove is a finite value in the thermodynamic limit at infinite times. And because of that, you would expect, well, perhaps the system is actually not thermalizing, and perhaps the claim of dipole conservation leading to localization is true. And if you look at the profile, you will find that the profile is indeed exponentially localized around the initial point. So we will find that the reason for this in the next slides is the phenomenon of so-called Hilbert space fragmentation. But in general, if you add some additional, say, longer range term, in particular here this H4, the system will simply relax. So it will really thermalize, but it will do it in a really slow way. It will do it in a way that you can describe by using hydrodynamics. So, yeah.
I'm sorry, so as far as this has numerical result, right?
This, right.
Now that's the question, so these two limits don't commute in your case, or do they?
Which two limits?
L to infinity.
Right. One should, like, to make sense, one needs to take the thermodynamic limit,
yeah.
And then you take the time to infinity limit.
That's what you're doing numerically.
Yeah, this is what you, basically you don't rely, what this means in numerics is you don't rely on any data such that when you increase the system size, you don't see a convergence.
Okay.
So you want to converge in system size and you only look at time windows. Nonetheless, these data, these kind of lower bounds, you can show that semi-analytically. And this kind of a slow decay, you can also show that semi-analytically.
And why your noise increases with time?
Well, these are, like, say, so this is mostly based on the kind of Hamiltonian. It's not so much noise, it's the finite size effects. So the fluctuations of this will decrease with system size. Okay, and you can also tune parameters in your Hamiltonian to make it as small as possible. Okay, so in general, you will find the system will relax, although slowly. But for some reason, in some cases, you find that the system kind of has some problems to relax. And the reason behind that is this so-called Hilbert space fragmentation. So usually when we have conserved quantities, right, when we have a system, the first thing we do is we kind of pinpoint the conserved quantities. You would say, well, the system has charge and dipole conservation, and therefore once I fix those, and if I did a good job identifying my symmetries, everything should be, I should be in one symmetry sector. However, here, what you find is that even after you fix your charge and your dipole, your Hilbert space still kind of splits up into exponentially many subspaces, which are not labeled by a global conserved quantity or a local conserved quantity. So there's some additional kind of additional structure behind. And basically what this shows is that if you have, say, two states, this one psi 1, psi 2, they have the same charge, the same dipole, but the dynamics of the system is unable to connect them. So I will, if you want, I can tell you the reason behind this later on. But this, when this phenomenon happens, where the number of these sectors is exponentially large, we would say that we have this kind of fragmentation of the Hilbert space into exponentially many sizes. Just in comparison, if you have a usual conserved quantity, say particle number, right? Particle number has extensively many sectors, as many sectors as the system size. So that could only explain, say, polynomially in system size sectors. If you have exponentially many, there is something else going on. Okay? However, in general, if you kind of consider any dipole conserving system, such fragmentation will still occur, but now the largest connected component will be almost as large as the Hilbert space. And what you will find is that your system is behaving quite similar to a generic system. Okay, so in this case, all the states, or almost all the states in one symmetry sector will become connected. So what this gives you is you have a bunch of different kind of fragments or subspaces, which you can imagine as having completely different dynamics within each of them. Some sectors that are perfectly thermalizing, some sectors that might be localized, some sectors that may have some other kind of dynamics, and therefore there will be a strong dependence on the initial state that you consider. And finally, for those who are more into the out of equilibrium behavior, you can relate this to the physics of quantum any-body scars and this kind of physics. So it's related to that. Okay, so but in general, we will have this kind of division between a strong fragmentation that is likely to give you this kind of lack of thermalization features, but more generally, you will find weak fragmentation in the sense most of the states are connected and some of them are not, but the physics in the thermodynamic limit doesn't change much. Okay? Okay. So let me go. So, okay, so far I told you about the upper half of the kite. So we saw that the Hilbert space fragments into different sectors. Some sectors might be thermal, some sectors might give localized dynamics, or any kind of physics that you cannot tell by simply looking at local terms of your Hamiltonian. You need to work a bit more. And now in the second half, I will tell you how to get there. Look, I told you, imagine if we can impose such a conservation law. So can this ever occur in nature, or if it happens, in which scenarios do we expect it to happen? Okay, so this will be the next part. So what we did is, together with the group of Monika Eidelsburger in Munich, what they took in the experiment is consider ultra-cold atoms in an optical lattice. So what you have is two laser beams. You constructively interfere them. This makes you this kind of standing wave. And now you cooled down your atoms in this optical lattice and you trap them. You might have an atom with two internal degrees of freedom. Red and blue, spin up, spin down, something else. Okay? So now these atoms, what they can do, they can tunnel from one well to another with some hopping strength J, or they can interact on site with some interaction strength U. So what they just realized is the Fermi-Hubbard model. You have some hopping and some interaction strength. And now what you can do, you can apply a magnetic gradient field. So this basically tells you that as a particle, say, an atom moves to the right, they acquire some energy delta, some local energy delta, so it takes more and more energy to, say, hop to the right. You're applying, if you wish, you can imagine you're applying a uniform electric field. And this gives you this additional term in the Hamiltonian. So if you notice, this looks really similar to the dipole, to the conserved quantity I was talking about before. So if we simply now take, say, this energy term, or this term in the Hamiltonian much bigger than the rest, what you will find is that a single atom, right, is not energetically beneficial to hop up or hop down the lattice. And the only way to do so is by two atoms being correlated and hopping at the same time, such that the center of mass is conserved, and this will kind of keep this term of the Hamiltonian constant. Okay? So the dynamics in this large tilt regime, this is like a tilt, is given by an effective Hamiltonian that really looks like the effective Hamiltonian I was telling you in the first half, where you have some dipole conserving term acting on three sides with some hopping rate J3 and some higher order terms. So therefore, what you will find is that your dynamics, if you do this experiment, will be strongly dependent on the initial state, because at some certain time window, you will realize this physics of Hilbert-based fragmentation. So what we did is compare the kind of model, the simulations with the actual experimental setup, and try to get some insights into the physics, again, for those who are more into the topic of Stark MBL, like many-body localization and things that happens in this regime as well. So what they did is they prepared different families of initial states. Of course, depending on the setups, you can tune like how your local degrees of freedom look like, but in this case, they can just make this transitive wave, these nil states on even sites with kind of random local magnetization. They prepare such an initial state. They tune different regimes of the tilt and interaction strength, and then they let the system evolve. And they look, say, the trace of a given observable, in this case, the imbalance, which measures the number of atoms in even and odd sites, and they let the system evolve. And now you can ask questions about this saturation value, and then you can say, well, if the system were to thermalize, I would predict this saturation value. If you see something different, it signals that at least for the time scales they measure in the experiment, this is not what the system is doing. So basically what they find in the experiment is that indeed it looks like the system is not thermalizing, and we connected this to the presence of Hilbert fragmentation and this strong dependence on the initial state. So they look at different regimes, not only this large tilt regime that we just discussed, but different regimes where kind of similar kind of physics happens, these different kind of kinetic constraint models can happen. And in general, you find, at least for the time scales of the experiment, which, by the way, are pretty long. They can go like hundreds of tunneling times, which is quite surprising. They find kind of similar features. And as I said, this is kind of relevant for the study of this kind of many-body localization that was suggested in a similar experimental setup. So,
Can you actually, explain a little bit more what's in that plot?
In that plot, oh, right. So in this plot, it contains the traces for the imbalance. So the imbalance, again, is the number of atoms on even sites minus odd sites. The reason why they look at these quantities is because they have like optical lattice with double well, and then they do this free. And this is the domain. This is the doublon imbalance. So they can measure like number of doublons. This is synchlon without checking the spin. And this basically shows the different signatures for doublons, synklons, and this is for the kind of generic imbalance for zero doublons. They can also kind of penalize having two doublons at all times. Well, actually, no, this is the density, zero doublons in initial state. And basically what they look is different regimes as a function of interaction strength and the tilt. They look at positive interaction strength because you find there's some dynamical symmetry in the system. So this part is the same as this part. And what they look here is the saturation value of the imbalance after, I think, it was 100 tunneling times or so. And they look at this as a kind of a phased diagram of the behavior. And what is surprising is that even for rather small tilts, you would have expected that after so long times, I mean, you should see something flat at zero, but it still looks like it's completely stuck. And then some people have claimed Stark MBL physics, but here we don't have enough kind of results to claim that is the case. Could be consistent to that, but it's not necessarily the case. So yeah.
Is it clear why there's an increase on the saturation around 10?
Here? Well, you can understand these lines as resonant processes.
In the middle between, yeah, like around 10, 11.
I think the way I see the plot is opposite. It's not so much an increase, but a decrease at these 2 points.
Okay.
At these 2 points, you have a resonant behavior. And it happens that the middle is larger. But okay, so let me briefly jump back to kind of theory walls, and this is kind of relates to a recent work that puts out. So there was a recent work that was really nice because what they did is, okay, let me try to give a mathematical framework to deal with this fragmentation business. Let me try to give a mathematical framework such that once we understand the basics, we can come up with different models. We can understand what is the necessary ingredients that we need. So the observation they made is like, we have considered a Hamiltonian, and I tuned this hopping to be uniform. But actually, as you saw, when we have conserved quantities in condensed matter, it's because every local term of your Hamiltonian, right, commutes with the conserved quantity. So you can put here, say, any random coefficient you wish, and your structure will be the same. So give this observation, you say, okay, let me formalize a bit more. Let me consider the algebra of all local terms. Let me call this the Bond algebra. So this is whatever combination or multiplication of these terms. And then I'm going to have the commuted algebra. This is a set of all observables that commute with every local term of this set. So now, basically, fragmentation means that this algebra is exponentially large. So you can connect the two things. It's a bit more involved, but basically, if this is exponentially large, if you can find exponentially many operators that commute, they may be non-local, but you can find them, then your system is fragmented. So in particular, what we saw before are cases where this fragmentation, you can think of projections on the set basis. Okay, so it's things that are really diagonal in some product basis. And from this point of view, it looks really classical. No, you could say, well, I can come up with a classical system doing the same. I don't need quantum for this observation. So basically, you can connect these bases to some kind of what happens at this level. But because of this observation, you can also ask, can I find a fragmentation that is actually unique and entangled basis, where this happens in a highly entangled basis, and I will have problems to find a classical system having exactly the same structure. So what we consider is this kind of two regimes of an entangled basis, a classical basis, and then we say, okay, imagine you have that. Would you be able to distinguish them? Would you find any observable that can tell apart if you are observing one or the other? And you can try to do this exercise, and actually, it's not easy to come up with something for closed systems. So what we did is, okay, let us couple it to a bath. So let us consider open quantum system. So let us couple to a bath, and let's look at the evolution, say, from some initial state that we prepare, and let's look at the structure of the density matrix that appears. Let's look at the entanglement of the density matrix and see whether we can relate entangled basis, non-entangled basis, with this being more entangled or not. So in particular, what we look at is entanglement negativity, which is a measure of entanglement in open quantum systems. If you have open quantum systems and you look at volume and entanglement, it will mix classical correlations with quantum, so it won't tell you much. So you need to look at something else. And when you do that, what you find is that in the classical case, well, you couple to a bath, so correlations just kind of quantum entanglement decays. It just vanishes, and your system looks pretty much like an ensemble of different configurations. But in the case of quantum fragmentation, what you will find is that actually your negativity is still volume law, meaning it scales with the volume of the system. So the stationary state is still highly entangled. And this is because the basis where this fragmentation happens is kind of really highly entangled basis. So it was a bit, this last part might have been a bit fast, so I'm happy to go over questions in more detail if you are interested. But the main conclusions I want to tell you is that what we learn is that symmetries, either approximately or you impose them artificially, and you can think how it really imposes constraints on the dynamics of the system and can actually hold thermalization. You can find really easy experimental realizations. You don't need to engineer much. You put a tilt, you crank it up, and this is your approximate behavior. Because of this, we learn about the structure of symmetries. What does it actually mean to have a symmetry in a condensed matter setup in a many-body system? And finally, we kind of try to distinguish and learn about this distinction between quantum and classical fragmentation. So this was an accumulation of works with the people in Munich, both in theory and experiments. And with this, thank you very much for your attention. I was first.
We have time for a quick question.